ladies and gentlemen of the audience, today I'm going to be talking a little bit about something that I personally find extremely fascinating and something that is forever growing and ever changing. In 1951, Albert Einstein attempted to prove something that he thought would never be able to be proven. Something as small as, let's say, a marble out in space can have enough matter and energy to warp the fabric of space and time. Now, simply all that is something that is known as the theory of relativity. And that's exactly what I'm going to be talking about today. And all that is something like an object, whether it be super small, super big, but it has such a mass and such a gravitational pull that it can bend. Now, in order to really understand that, I'm going to be talking about something that truly has an extreme amount of mass that is known, that we truly only know is to be one thing, and that would be the black hole. Albert Einstein had a theory about something like that, that something in outer space could have enough pull and enough bend to move objects around. And we truly didn't know what that was until studying recently. 1971 is when the first black hole was discovered. And some of you might be asking, how exactly did we discover a black hole? Since it's just a piece of black sheet that we can't really see with the naked eye. Simply because it pulls and bends things around it, such as light and dust and other particles. That's exactly how we saw a black hole, and that's how we figured out that something like that existed. Now, for just a simple reference, a black hole has about 1.2 newtons times 10 to the 44th amount of pull and gravitational force, and that is a lot. That could probably swallow a lot of things, including yourself, and kill you. Unfortunately, kill you. But as I was saying, not even light can escape a black hole, and to our knowledge, light is the fastest thing on Earth, and that's going to be a key portion later on. So the life cycle of a black hole is also kind of important because there's stages of a black hole that have more force and more pull. So to simply start with a black hole, it starts with a star that slowly dies off. Eventually our sun will do it, and a lot of other stars, of course, will eventually die, but not all of them turn into black holes. They have to die in a certain way to where they leave just a small amount of matter that has such a great amount of gravitational pull that it slowly sucks things in and causes it to grow and grow and grow. Now, black holes can also die, which is also another key important part, because when they die, they actually swallow themselves whole, and then they just start that life cycle over, but they become bigger and bigger with that. There's a lot of things that we also don't know about black holes, and that's just the theory of what kind of happens. It's called Hawking's theory, and it was made by Stephen Hawking. So, turning to his theories itself, he has two parts of his theory. He has general relativity and special relativity. I'm going to be talking about both, but I'm going to start with general relativity. General relativity is simply something that we experience every day in our day-to-day life, and well, you might not notice that you're doing it. I'm going to just start with a simple visualization. Just think about this for a minute. There's a trampoline. You have a marble. That marble can be anything out in space, or the planets, asteroids, anything. You roll that across that trampoline, it'll just keep going and keep going. Nothing to stop it. But you add something in the center of that trampoline. Take a bowling ball, for example. Has a decent sized mass compared to that marble. You roll it, it's going to pick up the orbit and go around and around and around. That's simply all his general relativity is talking about. An object that has such a large amount of mass can bend the space-time, aka the trampoline sheet. Now, that big mass can be anything. You can be that mass, the sun can be that mass, the earth can be that mass. Any object that has life, frankly anything, has a sort of mass and a gravitational pull. It's just really hard to notice unless you talk about it on an astronomical scale. That's why I mentioned the black holes, because those, to our knowledge, have the most gravitational pull. All right. Now I'm going to also I'm going to shift to his special relativity. Special relativity is a little bit more complicated, but I'm sure you all have at least seen it in some form. I'm assuming everyone here has at least taken a physics or a math class in their day. And there's an equation that he in fact talks about and is mentioned in special relativity that I'm sure you've seen, but you don't exactly know what it means. It's E equals mc squared. Now, if you don't, you know what that means. It's energy equals mass times the constant of the speed, whether that be the speed of light, speed of sound, or you just move it. Now, a lot of people use that incorrectly, especially in physics class, because they don't talk about that in space. But in reality, that equation is meant to be used for aeronautical space travel. So, simply, that can be used for a lot of things in space. When he was talking about his theory, the special relativity theory was talking about the ability to ignore and evade gravity. Now, a lot lot of you think that's not possible. Maybe you think that's not possible, but in fact it is. You can do it, frankly, standing here on Earth. You just do it in a small amount. If you jump, you technically are evading gravity for a short period of time. You just don't realize it. There's a point where you hover, and then you come back down. But the Earth's gravity is too strong, and you are not strong enough to push yourself up high enough. But what if I told you there was a way that we can avoid gravity, but not here on Earth, but out there, and we've done it many, many times? It's simply space travel. Take any rocket, for example, that we sent in outer space. There's only one possible way that you can avoid it, and it's using a special relativity theory. You have to put enough force to avoid gravity, which is simply just E equals mc squared, energy times mass times the constant of acceleration. Now I'm going to go back to that same visual representation of that trampoline and the marble with the bowling ball. You take that marble and you roll it. It's going to do the same thing. But if you put a little bit of force on that marble, what's going to happen? It's going to completely avoid that and continue to go in the straight pattern that it was. It might deviate a slight amount, but such a slight amount that's not noticeable, especially when you're talking about it on a large scale. Now take something that's even bigger, like a tennis ball, for example. You have to now put less force on that tennis ball to avoid gravity, but of course there's the counterpart where if it's too heavy, you have to use more force. So it's about finding that sweet spot. But with that sweet spot, he was able, with that equation and finding that sweet spot, we were also able to explore many, many things out in outer space due to that. Take, for example, anything that we've sent to the moon, past the moon, or simply out of orbit, we've used his equation. Now, I'm going to be talking about why exactly I brought up a black hole in comparison to these things. So there's a lot of theories that revolve around black holes. Some people claim that they can be folded and warped so we can go through them if we can somehow survive and it'll take us somewhere else. But Einstein's theory talks a little bit more when it came to black holes about what it can do if we are able to harness the pull and gravitational force of it. Now, again, like I said, the speed of light is the fastest thing that we know of on Earth, and his equation equals mc squared also proved that there's nothing that can possibly go faster than the speed of light, which, to our knowledge, is true. So if nothing can go faster than the speed of light and it can't escape a black hole, what possibly, what does that mean with a black hole? Well, the black hole is simply, all it means is that it's just his whole theory. It simply is just molding space and time and folding it all into a small, dense area of nothingness. Nothing can frankly escape it. It's all folding in on itself consistently. That's why eventually they fold in on itself and die. It's because it's sucking everything in and folding it like a piece of paper. But what can happen if we somehow manage to harness that energy? If we somehow could harness that energy? Well, simply anything. It's an unknown. That's why his theory is still a theory. It's because we don't know what will happen. We can't prove it yet because we don't know anything past